Hello, I welcome you all to this channel. This is my third video on lanthanoids. If you have not watched my first two videos, please do watch them and then you can come to this third video. So in first video, I have briefly introduced you to lanthanoids and then remembering their electronic configuration and remembering the name of lanthanoids. In fact, it's a trick kind of thing that has been described. And in the second video, this an oxidation state and lanthanoid contraction, those aspects has been taken and related to these two things, even some CSIR net questions, even those questions have been discussed, and for that I have made one more video. So in that way, this is the fourth video in this series. So in this particular video, we'll be looking at the coordination chemistry of lanthanoids, briefly some important points associated with coordination chemistry, magnetic properties, and absorption spectra of lanthanoids, mainly keeping CSIR net examination and previous appeared CSIR net questions in mind. Okay, let's begin. First, we shall start with coordination chemistry. So coordination chemistry of lanthanoids, if we consider, these are 4f series elements, therefore metal orbitals that can be considered for mainly the metal orbitals which are considered for bonding, they should be 4f. And now in total we have 7 4f orbitals, therefore coordination number that will also increase when it is compared to d block or transition metal coordination chemistry. This coordination chemistry is completely different. In case of d block coordination chemistry, as we know, coordination number of 4 and coordination number 6, that is common, but here it is not so. So usually it will be 6 or more than 6 itself. 6 itself is rare. More than 6, it will be common. So we can have coordination number of 6, 7, 8, 9 up to 12. We can observe coordination number. Next thing here, the geometry, it is not fixed. In case of transition metal complexes, we have preference for a ligand, and for a given metal system we can say that geometry it will have some preference, but here it is not so. Here you can say the geometry it will be flexible, and definitely there are reasons for this. First thing, in this case, bonding interaction between metal and ligand, it is considered to be much ionic in nature. It is just ionic interaction rather than covalent interaction, right? So it's much ionic, and we can say ML, metal to ligand covalent interaction, to be very minimum in this case. That is first thing. And second thing, this 4f orbitals being buried, this LFS effects, ligand field effects. So which kind of ligands you are taking and how they affect the complex, that point it will be having minimum effect. And LFSC, it will not decide geometry. So in case of transition metal complexes, depending on LFSC, if greater LFSC is there for some particular geometry, in that case you can expect it, expect the metal to go with particular geometry. But here that kind of thing is not there. So because of these two reasons, geometry you can say to be flexible. And the different kinds of geometries they are possible. Say it starts from trigonal prismatic, trigonal antiprism for coordination number 6, and then square antiprism for coordination number 8. Then this is usually most common for earlier lanthanoids. Even when they form water complexes, 9 water molecules, then they can coordinate, and usually it results in tri-capped trigonal prismatic. So I request you all to search for these geometries in internet and just make familiar with this kind of geometries. So this is for coordination number 9, tri-cap trigonal geometry, and similarly icosahedron for coordination number 12. You can expect icosahedron geometry, and different kinds of geometries they are possible. Next, this higher coordination number, it is observed for large metals. Say in the beginning of the series we have lanthanum, cerium and all. So these kind of metals, they will have preference for large coordination numbers, because relatively the size of metal ion, it is large. And of course that is one reason, but not with all kind of ligands we can expect this large higher coordination number. Usually with small ligands like say fluoride and all, we can expect this, or even oxygen donor water molecules, small ligands, we can expect higher coordination number. Next, which kind of ligands are involved? If we compare to transition metal coordination chemistry, in case of transition metals, nitrogen donors, they are most common. Even complex of Br minus I minus, that can be found in case of transition metal complex. But here much preference is there for ligands such as F minus or oxygen donors, say hydroxide ions or water molecules. Even if nitrate, if it is acting as ligand. Say most of the times we will be taking lanthanum nitrates to prepare the complexes. There, nitrate ion using its oxygen. Here you can expect two oxygens to be coordinated simultaneously to oxygen. Preference will be there for oxygen coordination over nitrogen. Even in some cases, even chloride coordination it can be expected. And reason for this preference over ligands is because of this Ln3 plus. They act as hard acids according to HSAB principle. So all these Ln3 plus ions, they can be considered to be hard acids. So we can find higher charge is there, and higher charge, smaller size, or if the metal ion, it is difficult to ionize, in that case it will behave as hard acid. So being hard acid, it will have preference for hard bases. So all these ligands, they come under the category of hard bases. Therefore hard acid hard base interaction is preferred, and these kind of ligands will be usually involved in coordination rather than nitrogen, bromide, iodide, soft base kind of ligands. Right. Then last thing about this, there are so many things, some important points I'm providing here. All these complexes, they undergo very rapid ligand exchange reactions. In case of coordination complexes, ligand exchange reactions, only for few cases it will be very rapid, whereas otherwise some complexes, they show inert behavior. They will not undergo ligand exchange reactions that fast. But here ligand exchange reactions, you can expect them because interaction is not much covalent kind of interaction, and it's being ionic interaction. Ligand exchange reactions, they are common. Okay, these are some points in connection with coordination chemistry or coordination behavior of F block elements. So if you need a comparison, you can just refer to Hui book. Hui book, he has just compared nicely the difference in coordination behavior of transition elements as well as this inner transition elements. Okay, go to the next property. Next property is absorption spectra or electronic spectra. In case of D block elements, it is the transitions we say due to DD transitions. Similarly here, absorption spectra mainly it will be because of FF transitions. Just like our DD transitions, even we can have these FF transitions. But FF transitions, they are completely different from DD transitions. So in which respect or in what respect they differ, that we can see. First thing, FF transitions compared to DD transitions, they are weak, right? Of course, DD transitions are itself weak, but FF transitions, they are said to be further weak, right? And the reason being same, Laporte forbidden transitions. These FF transitions, they are Laporte forbidden transitions. Even DD transitions, if you remember, they are Laporte forbidden itself, but there, because of ligand vibrations, some kind of relaxation, Laporte relaxation, it will be observed, because of which Laporte rule to some extent, even in case of octahedral complex, to some extent it will be relaxed. And the important reason being ligand vibrations. But here now, in case of F block elements, F orbitals being buried, F orbitals, they will be say 4F orbitals we are taking, beyond which you will be having 6S orbitals and 5D orbitals, or 5th shell, 6th shell will be there. So we can say this 4F orbitals being buried, so they are not much affected by ligand vibrations. Ligand vibrations, it will be taking place at the outer radial part of the atom. That will not seriously affect FF transitions, and because of this reason, vibrational relaxation, it will not be observed. So this F orbitals, they will be purely F orbitals, and so FF transitions, if you consider FF transitions, they will be completely Laporte forbidden, and that's how they will be weak. And one more characteristic feature of this FF transitions, unlike DD transitions, these are very sharp. DD transitions, they are broad. We know in electronic spectra of DD electronic spectra of coordination complexes, we have seen say broad transitions like this we observe in case of DD transitions or coordination complexes of transition matrix. But here say something like this, very sharp transitions and many transitions. Compared to the number of transitions that are observed in coordination complexes, even number of transitions it will be more in case of this F block complexes, right? Again, reason being same, the sharpness, it is due to F orbitals being buried. F orbitals being buried, they are little affected by ligand vibrations. And this broadness in case of DD transition, it was mainly due to this vibrations associated with ligands that used to make the transition broader. But here, so these ligand vibrations, they do not affect F orbitals. That's how these F orbitals, they are free from ligand vibrations, and transitions you can expect it to be more sharp transitions. Number of transitions, it's more because here you can have so many microstates, and because of so many microstates, so many states will also be possible. So because of that, you can say that the number of transitions will be more. Fine. Next, FF transitions are insensitive to ligand environment. This point it has been mentioned because ligands, they will not be affecting F orbitals much. Therefore, FF transitions, they are insensitive to ligand environments. Again, reason being same, F orbitals being buried, right? And because of all these reasons, these lanthanum 3 ions or their corresponding solutions, they will be very pale in coloration. But sometimes intense coloration is also possible. Little intense coloration is possible, but that will not be usually observed with Ln3 ions. It will be observed with Ln4, like say cerium. You can show a oxidation state of 4 plus there, or some other lanthanoid which can show different oxidation state like 2 and all. In that case, some charge transfer transitions, they are expected, because of it some intensity can be gained for these compounds. Okay, that's about absorption spectrum. And lastly, we can see something about magnetic properties of these complexes. Again, same thing here. These magnetic properties, are insensitive to ligand environment. So in case of transition metals, ligand, it can decide the magnetic property. Ligand, it can make the complex low spin, high spin, and those kind of things are possible. But here ligand, they will not decide the magnetic property. It's because ligand to 4F interaction, it will be very less. It will be just ionic interaction, and therefore ligand environment, it will not affect magnetic properties much. So magnetic properties of complexes and magnetic properties of free ions, if you consider, so they will be comparable. No much difference can be observed. Next thing, so in this case, these are heavy metal ions, therefore spin orbit coupling, it is very large, and therefore while calculating theoretical magnetic moment, we should consider this spin orbit coupling too. And in magnetic properties of coordination complexes, this point has been described. If you have not watched that video, magnetic properties video, definitely you can watch. You can find that here, because of spin orbit coupling, given this J, it should be considered, and the corresponding formula to calculate the magnetic moment, theoretical magnetic moment of lanthanoids, usually it will be this formula. G is equal, this one, mu is equal to G into square root of J into J plus 1, where this G is Landau splitting factor, right? And much of the lanthanoids, the calculated magnetic moment, it matches well with the experimental magnetic moment, with the exception of few. So which are those exceptions? We shall see that, right? So here one point to be remembered, this formula, it can be adopted when ground state is populated at room temperature. So what I can say is that metal ion, it should be in ground state at room temperature, right? So then just based on the ground state, what is the term symbol for that ground state, or what is the capital L value, S value, J value, all those things can be calculated, and they can be substituted accordingly, and magnetic moment can be calculated. Lanthanum 3 plus and lutetium 3 plus, they are diamagnetic. This is quite expected because lanthanum 3 plus, it will be F0 system. You can write the electronic configuration and you can just check. Whereas lutetium 3 plus, it will be F14. So you cannot find any unpaired electrons, because of which they will be diamagnetic, right? And next thing, very important, so many times this has been asked. So in particularly pertaining to F block, questions are being asked like 4 statements they'll be giving, and out of those four statements, which statements are correct? Those kind of questions have been asked in CSIR NET. So many questions are of that kind. So there definitely one point, it will be in connection with this magnetic moment of samarium 3 plus and europium 3 plus. Remember this fact that samarium 3 plus and europium 3 plus calculated mu from this G into square root of J into J plus 1 formula, it differs from mu experimental. Mu experimental, it will be different here. So you cannot correlate mu experimental with mu calculated from this formula, right? Reason being, in these two cases, so as I have said, this formula, square root of G into square root of J into J plus 1, this formula, it is adopted when the ground state is populated. But in these two cases, what you can expect is at room temperature, even first excited state, it will be populated. So if you make use of this formula, you will be taking into consideration ground state G value, ground state J value, or ground state L value and ground state S value will be taken into consideration. But at room temperature, even if first excited state is populated, then what you calculate from the values of ground state, that will not hold good, definitely. And for this reason, you cannot make use of this formula, or even if you make use of this formula, the results they will not be accurate, especially for these two ions, samarium 3 plus and europium 3 plus ion. And even in this case, LS coupling it is not large. So this formula it can be adopted when LS coupling it is sufficiently large. So when LS coupling is there, then only we can go with this formula. If LS coupling is not there, then other formulas are there. So in this case, LS coupling it is also not large. Because of this reason, this formula it will not yield you good results in case of lanthanum 3 plus and lutetium 3 plus ions. Okay, there are good number of questions. I can find some 7 to 8 questions in CSIR NET pertaining to mainly these three aspects: coordination compounds, absorption spectra, and magnetic properties. So in one more video, in a separate video, I'll take all those questions, and even solutions to all those questions it will be provided in that video. Okay, thank you for watching this video. If you feel that this is useful to you, please share this video with your friends and give a like to this video, and please express your opinion in the comments section. Thank you for watching this video. Thank you again.